Let's solve a spring oscillation problem involving period and maximum speed. We have a 3 kilogram mass attached to a vertical spring with spring constant 150 newtons per meter and amplitude 0.08 meters. First, let's understand the physics of simple harmonic motion in a spring system. Springs follow Hooke's law, and when displaced from equilibrium, they oscillate in simple harmonic motion. The restoring force equals negative K times displacement, where K is the spring constant. An important property is that the period depends only on mass and spring constant, not on the amplitude of oscillation. The mass oscillates between maximum displacement positions, passing through equilibrium, where velocity is maximum. Now let's calculate the period of oscillation using the spring mass formula. The period formula for a spring mass system relates mass and spring constant. T equals 2 pi times the square root of m over k. We're given mass equals 3 kilograms and spring constant equals 150 newtons per meter. Substituting our values, T equals 2 pi times the square root of 3 over 150. This simplifies to 2 pi times the square root of 0.02. The square root of 0.02 is approximately 0.1414. Therefore, the period is 0.888 seconds, or about 0.89 seconds. This means the mass completes one full oscillation cycle every 0.89 seconds. Next, let's find where and how the maximum speed occurs. The maximum speed always occurs when the mass passes through the equilibrium position. This graph shows position versus time. Notice that when position crosses zero at equilibrium, that's where velocity is maximum. Conversely, at maximum displacement positions, the velocity is zero, as the mass momentarily stops before changing direction. Now let's calculate the maximum speed using energy conservation and kinematic equations. We can use energy conservation. At maximum displacement, all energy is potential. At equilibrium, all energy is kinetic. 1/2 Ka squared equals 1/2 mv max squared. Solving for versus max, we get Vmax equals A times the square root of K over m, with amplitude 0.08 meters, spring constant 150 newtons per meter, and mass 3 kilograms. Vmax equals 0.08 times the square root of 150 over 3. This simplifies to 0.08 times the square root of 50. The square root of 50 is approximately 7.071. Therefore, the maximum speed is 0.566 meters per second, or about 0.57 meters per second. Let's verify this result using angular frequency, which provides an alternative approach. Angular frequency, omega, equals the square root of k over m. Omega equals the square root of 150 over 3, which equals 7.071 radians per second. Maximum velocity equals amplitude times angular frequency. So Vmax equals 0.08 times 7.071, which gives us 0.566 meters per second, confirming our previous result. Both methods give us the same answer of 0.57 meters per second, which validates our calculation. Let's understand what these results mean physically. The mass moves fastest at equilibrium with speed 0.57 meters per second and oscillates with amplitude 0.08 meters. A period of 0.89 seconds means the system oscillates at a frequency of about 1.1 hertz, or slightly more than once per second. Throughout the motion, energy continuously converts between kinetic energy at equilibrium and potential energy at maximum displacement. Let's summarize our complete solution to this spring oscillation problem. The period of oscillation is 0.89 seconds. The maximum speed is 0.57 meters per second. This maximum speed occurs as the mass passes through the equilibrium position. The key formulas are T equals 2 pi times square root of m over k, and Vmax equals A times square root of k over m.